Hello physics students, and welcome to a short lecture on friction. In this lecture we're going to talk about what friction is, different types of friction, what affects the amount of friction between two surfaces, and finally we'll talk about calculations involving our friction equation. So first of all, what is friction? Friction is a force that always opposes something's motion. It forms because surfaces are uneven, and when they're pressed together, these surfaces do not, there's resistance to them sliding past each other. This is very obvious with rough surfaces. You know, if you had wood dragging across carpet or sandpaper, but even ice or oil or the smoothest surfaces you can think of at an atomic level are rough surfaces. So friction is a force that opposes things in motion. There's several different types of friction. The first one we're going to talk about is static friction. So again, there are micro welds that have formed between this box and the floor, and when you go to push it, those micro welds oppose the box's motion. Static friction, static means stopped or stationary. So it's the frictional force between something that is stationary and the surface it's touching. If you were doing the friction lab that we did in class, and you had your force meter, and then you were going to try and pull the block, the force meter would first, of course, go along reading 0, and then as you started to pull on that block, the force would increase, and then all of a sudden at some point that block would move, and then that should have spiked and then gone down to a new level, and then of course if you stop pulling it would go back down to 0. So what are we looking at in a force graph like this? So this would be force over time. This spike would be the static friction force. It was the amount of force it took to break those original welds down here and get that object to move. Sliding friction, on the other hand, once it starts moving, is actually less than static friction. So, second type of friction, sliding friction. Something that is sliding, again, still has friction, but it's a little bit less than static friction. So sliding friction is less than static for any two surfaces. Okay, and then finally another type of friction we're familiar with is rolling friction. And rolling friction is less than sliding friction, which is of course less than static. Which is why the wheel was such a great invention. It can make work a lot easier by reducing the amount of friction between two surfaces. Ancient Egyptians used to build devices like this to move really heavy rock blocks for the pyramids, and of course we use them in all of our bikes, cars, and rolling objects today. And finally, one more type of friction that is probably one we don't think of as much is fluid friction. So fluid friction is the friction that opposes motion when something is traveling through any fluid, such as water. This shark traveling through water, there are a bunch of water molecules floating around in there, and the shark actually has to push those molecules out of the way to move through the water. So when something moves through, it has to scatter these molecules, and that provides a resistance force and a fluid frictional force. It's obvious in the water that there's some friction there. Sometimes it's less obvious in the air. We're in air all day. Sometimes we don't notice it. But if you've ever been driving in your car and stick your hand out the window, you're going to feel that air resistance force very well. So the air is not nothing. There is lots of molecules floating around in the air. There's oxygen gas, carbon dioxide gas, water vapor, nitrogen molecules, and all of those have to be pushed out of the way to move through it. So those are all fluid frictional forces. So air resistance is a fluid friction force. Okay, what affects the amount of friction between two surfaces? So the first obvious one is the two surfaces involved. A box is easier to push across an ice rink than it is carpet. We'll talk more about a coefficient of friction relative to different surfaces later. The other thing that affects friction is the normal force between them, basically the weight force. So if this is the force due to friction, and this is the normal force. As normal force increases, so does the frictional force. Okay, so they have a direct relationship. They are directly related. We would say that force of friction is directly related to the normal force. A little bit more on the normal force. So, what is a normal force? A normal force is a force between two objects that is completely perpendicular to a surface. So, any force perpendicular to this surface would be a normal force. Generally, on a flat surface, what that means is just your weight. So your weight force is equal to your normal force. When are they different then? Well, let's consider a situation where something is sitting on a slope. So let's say this box, let's consider this box on a flat piece of ground and on a slanted piece of ground. So if this ground is flat, and let's say this box weighs in newtons 100 newtons, there would be a normal force and a weight force of 100 newtons straight down, if that's a 90-degree angle. But on this slope, the gravitational force is still straight down. So this would be 100 newtons straight down, but that force is not perpendicular to the surface. So you can actually break this down into two vectors, one that is straight down this way and one that is straight sideways here. And you can see that this force, which would be the normal force perpendicular to the surface, is less than this force, which is the gravitational force. So in this case, the normal force between this box and the hill would be less than the gravitational force of that box. And therefore, the friction between the box and this hill would be less between the box and this flat surface. Alright, the coefficient of friction. How do we find that? Well, there's no way to predict it. It has to be measured in the lab between any two surfaces. So basically what we do is we generate a graph where we put two surfaces together and we measure the frictional force for a whole bunch of different normal forces or weights. And we would plot these points, and these points would give us a line. We'd find a best fit line, if I can draw it here. Okay, far from a perfect best fit line, but you get the idea. And then we could find the slope of this line. Tells you the rate at which the frictional force increases as the normal force increases. And so that would be our coefficient. So our equation for a line is y equals mx plus b. In this case, because when we have zero weight, we have zero friction, our y-intercept is 0, and so we lose that, and it's just y equals mx, where y is the force due to friction, and x is the normal force, and m is the slope of the line, just like m is the slope here. So our coefficient of friction is basically the slope of a line that shows the relationship between the frictional force and the normal force. And we write that equation like this. Force of friction is equal to the coefficient of friction, which is this mu symbol, times the normal force between two objects. And again, this coefficient is unitless, and it's different for any two surfaces that are together. Okay, what about surface area? It's natural to think that more surface area would equal more friction. For example, let's say we had a block and we could place that block like that and drag it across the surface, or we could place it on end. Like this, and pull it across the surface. A lot of us tend to think that this block, because it has more surface area in contact with the ground, would have more frictional force. But it turns out, if we are careful with our experimental data, that's not true. This block and this block, as long as they have the same mass and they're made of the same material, or if this is the same block and it's just turned on its side, would actually have the same amount of friction. Again, the force due to friction would be the same. The coefficient of friction would be the same. And actually the normal force is the same because they weigh the same amount. This is supposed to be times there. Alright, so why doesn't it? Why doesn't having a larger surface area in contact with the ground increase the amount of friction? Well, it's because of the pressure, basically, the amount of weight per unit of area. So in this case, there's more total surface area touching the ground. And let's say we double that. What if we double the surface area touching the ground? Well, you'd think that would double the frictional force, but you're also cutting in half the amount of weight over that same area. So while this has more area touching the ground, this has more mass per unit of area, and so it ends up being a wash. The amount of friction would be the same for both surfaces. By the way, that can break down if we're talking about a really, really small surface area. So if you were to, for example, take this and turn it on edge like this, then you might actually get a small enough surface area that this point would actually dig in to the other surface, and that could increase the coefficient of friction between the two surfaces. That then would cause more friction. So if the area actually gets small enough that this thing forms a point and digs into the other surface, then smaller area would have more friction.